Hi, my name is Geordie Dalzell. I'm from RMIT University, and I'm here to present my group's work for the IEEE Generative AI Hackathon called Large Language Model for Extreme Electricity Price Analysis in the Australian Electricity Market. For this presentation, first I will introduce the background and motivation of this work. Then I will talk about the methodology, which includes market notice data generation and time series electricity price forecasting. After that, I will show the results from our empirical study, and I will provide some concluding remarks. In Australia, electricity is mostly generated, traded, and distributed through markets set up to match supply and demand. The National Electricity Market, or NEM, plays this key role for the eastern and southern parts of Australia. It is one of the biggest connected electricity systems in the world, with around 40,000 kilometres of transmission line, and it serves as about 9 million customers. It works as a wholesale market, making it possible for electricity to be exchanged between those who generate it and those who sell it across 6 eastern and southern states and territories. This accounts for about 80% of all the electricity used in Australia. And for retailers who sell electricity to consumers, coming up with a smart electricity trading strategy can significantly boost their profits. This means putting together a trading plan that's based on what they think electricity prices will be in the future. Because of this, having a decision support system for predicting electricity prices is crucial to their profitability. The national electricity market in Australia deals with extreme price volatility, with shifts from nearly zero to many thousands of dollars per megawatt hour. This variability is compounded by the diverse energy mix of aging coal generation and a high penetration of rooftop solar PV systems. This makes price forecasting particularly challenging. Traditional research focuses on broad time series predictions, but for electricity trading, pinpointing sudden price spikes is crucial for profit. Deep learning has emerged as a key forecasting method, but the unpredictability and complexity of market notices hinders accurate predictions. Advances in large language models offer new possibilities, as they can process market notices to enhance predictions under extreme conditions. This allows us to construct a decision support tool for traders navigating the volatile market. When there is a mismatch between electricity supply and demand, the Australian Energy Market Operator, AEMO, steps in by sending out lack of reserve notices to encourage more power generation. These imbalances can happen for many reasons, like unexpected or planned events taking generators offline or affecting transmission lines. Extreme weather events like heat waves, bushfires, floods, or storms, or key equipment being offline due to maintenance or failure are common causes of the lack of reserve. AEMO reacts to these situations by issuing a forecast lack of reserve notices based on predictions of shrinking generation capacity. According to economic principles, if the energy supply stays the same, but demand goes up, electricity prices are expected to climb. This price hike can be especially noticeable during lack of reserve events. Lack of reserve notice includes 4 critical pieces of information: the specific region or state where the lack of reserve event is predicted to happen, the expected timing of the lack of reserve event, which covers the date it's anticipated to start and end, along with the exact start and end times, the forecasted amount of capacity reserve needed during the event, and the minimum amount of capacity reserve that's expected to be available at that time. Our proposed methods framework relies on 2 main parts. The first is an offline task focused on pulling data from past electricity market notices. In this step, we gather and sort market notices by type, and then break them down into tokens and embed them. After that, a pre-trained LLM is fine-tuned to act as a set model for dealing with real-time notices, helping to structure the info contained in the market notices into a dataset for forecasting. This dataset, which is aligned to predicting electricity prices by time and place, boosts the forecasting model results significantly. The second part deals with online tasks, aiming to predict electricity price trends using a deep neural network. A complex convolutional neural network short-term memory setup is used, which is trained with historical price data. To To improve its ability to predict peak prices, it uses a wavelet decomposition at the input to pull out key features from past pricing data. These features, combined with the market notice data, feed into the neural network to forecast future prices over upcoming periods. In this diagram, you can see the offline tasks are highlighted in blue, while the online tasks are highlighted in red. Prompt engineering with large language models like ChatGPT-4 can effectively extract and structure information from lack of reserve market notices for neural network use, showcasing its utility in transforming complex data. However, ChatGPT-4's usage-based costs can add up, especially with the high volume of real-time lack of reserve notices from the Australian energy market operator. Open source LLMs like Llama, Bloom, and Falcon offer a cost-effective alternative. These models can be run locally to enhance data security and cost efficiency, albeit with a potentially lower performance compared to ChatGPT-4. This presents a balance between cost and computational effectiveness. Here is an example data set which includes market notices data. Once the notices data is extracted, the output of a fine-tuned LLM can be collected and used to generate a CSV file. The generated CSV file can then be combined with the electricity price dataset and input into the model. To better extract electricity price signal features, a wavelet transform is applied to split the original data into 4 types of signals with time frequency features. The CNN LSTM network excels at integrating time frequency features, and this model surpasses traditional frameworks by combining the CNN's pattern recognition with the LSTM's ability to capture long-term dependencies. With 2 one-dimensional convolution layers enhanced by batch normalizations for efficiency, it adeptly handles the complexities of price data, significantly improving forecast precision and reliability through its ability to represent spatial and temporal dynamics. For the empirical study, we applied the model to electricity price data and lack of reserve market notices from South Australia, covering the period from 1st of January 2023 to the 31st of December 2023. The electricity price data was collected at a frequency of 1 point every 5 minutes, and we set a peak electricity price threshold of 4,000 Australian dollars per megawatt to identify periods showing price spikes. For these same periods, we also collected a total of 40 lack of reserve market notices. These data and notices were split, with 32 or 80% used for training and the model, and 20% reserved for evaluation purposes. The evaluation loss, shown in this figure, displays a steady decline from the first step of training to the last, indicating the model's increasing accuracy over time. Fine-tuning the large language model required substantial computational effort and time, which is why training was stopped at 450 steps. However, additional training could further decrease the evaluation loss, implying that the model has not yet reached its full potential in terms of accuracy. These 2 figures show the results of our empirical study, which we conducted for South Australia and New South Wales. The market notice period is highlighted in red on each plot. We can see from the difference between the green and black forecasts that the forecasts adjusted with market notice data are far closer and more representative of the real price data, which is shown in blue. In this study, we've introduced a cutting-edge decision support system designed to predict electricity prices during extreme conditions. The system features a wavelet transform CNN LSTM network architecture specifically for forecasting peak electricity prices. Alongside this, we've categorized electricity market notices and employed fine-tuning to refine a pre-trained LLM for the extraction and creation of a well-structured dataset. This dataset, derived from market notices, has been instrumental in boosting the performance of our wavelet transform CNN LSTM model and its ability to forecast peak prices accurately. When tested against real-world data, our findings highlight the LLM's capacity to process and organize unstructured data into a coherent dataset, and it significantly improve the efficacy of existing machine learning operations. Thank you for watching.